coming lecture, the next lecture would be all about some advanced concepts of TCP and just a small recap first that what we have already done. In first module, we have seen connectionless and connection-oriented multiplexing and demultiplexing. We understood the concept of ports. Then we have seen user datagram protocol, UDP, the concept of pseudo header and checksum. And then we, just a minute. I'm class. Then we developed a protocol using finite state machine, reliable data transfer protocol. Afterwards, we have seen pipeline protocols, go back and selective repeat. In second module, we have seen TCP in detail, TCP header, the usage model, the connection establishment, data transport, connection termination. We have seen TCP flow control with sliding window concepts and acknowledgement dynamics. Then TCP congestion control, that is slow start, congestion avoidance, fast retransmit, and fast recovery. And finally, we have seen TCP variants or different implementations of TCP which have evolved with time. Tahoe, Renault, New Renault, and TCP SAC. Now, in this module, we are going to have two lectures, maybe one more lecture, depends upon how fast we can go. Now, when sender can trigger, we haven't discussed up till now. Fine, that is the biggest question. And if you don't have any control, then it may lead to a very popular concept known as silly window syndrome. And then how to avoid it. And in TCP history, evolution of TCP timeline, we have seen Nagel's algorithm sometime. So we'll see silly window syndrome issue and how to avoid it using Nagel's algorithm. I told you that 32-bit sequence number space may not be enough. And because this sequence number space is wrapping around, it's a circular sequence number space. So how can we provide protection against wraparound? Similarly, window size of 16-bit is not enough. So how we can utilize window scaling option? And then the most important part, adaptive retransmission. How to choose and how to select, how to configure the retransmission timeout value. So again, we'll start from the beginning, the original algorithm, the Can-Practice algorithm, and Jacobson-Carroll algorithm. So this is about the implicit way of doing the congestion control. Then we have some implementation like explicit congestion notification, TCP read, TCP randomly detect, and DECBit was again a different protocol from a different uh, vendor or OEM, but it is very relevant when we talk about network assisted congestion avoidance. So up till now, network was not giving any explicit feedback. So in this mechanism, network can provide feedback explicitly to the TCP so that TCP can tune and start congestion avoidance. And then finally, we'll be seeing the source-based congestion avoidance, that is TCP Vegas. So this is what we are going to see in this lecture and coming lectures. And with this, TCP will be over. Triggering transmission, that's a big question. And let me take the full screen snip and we'll discuss about this then. Now, what is happening? Application keeps on writing bytes to the socket, to TCP. Now, the question here is when to send, when to trigger the sending process. Is after 2 byte, 4 byte, 6 byte, 8 byte, whatever. When to trigger this send? That's the question. Suppose window was closed. So in the previous window advertisement, suppose window was kind of near to zero. So in that condition, TCP sender keeps on accumulating bytes from the application. Now some acknowledgement, new acknowledgement received, which suppose opened the window for half of MSS, maximum segment size by 2. Now the question here is, should sender send now or wait for window to open more? Please try to understand the concept. So up till now we have talked about the like receiver is advertising window, remaining buffer size. But things are not happening in a discrete manner. So look, everything is kind of a conveyor mechanism that application is writing data, TCP is sending data, receiver is receiving data, sending acknowledgement, and advertising the remaining buffer size. Meanwhile, TCP is accumulating data, again send data, and this kind of thing is happening in a continuous manner. Now the question here is when to trigger, when to decide to transmit the segment. Or in other words, should my segment be having half of MSS, quarter of MSS, or 2 bytes, 20 bytes, 40 bytes? So if you talk about original specification, it was silent about this point. So there was no kind of indication given in the initial RFC that any control or any mechanism from the sender's perspective that when sender should start transmitting or trigger the transmit. Because for triggering, you have to pack the bytes into a segment, deploy a TCP header, and then only you can send. So how much bigger your segment can be when you have decided to send it? So there is a dilemma. Either you can wait for some more acknowledgement so that you can pack more data into one segment, hoping that in next acknowledgement you'd be getting more open window. So this is a issue that when to send or when to actually trigger the transmit. Now, if we talk about early implementation, they aggressively took advantage of any available window. So whatever window is getting advertised, if you have that amount of data accumulated, send that. Now let's see what it can lead to. What it can lead to. So in early implementation, suppose you are sending my advertised window of say 20 bytes. 20 bytes. So you advertise this window. Sender has sent 20 bytes. So those 20 bytes will be received. Fine. 20 bytes will be received. 20 bytes will be acknowledged. Meanwhile, maybe the window is not opened. So those 20 bytes will be received by the application. So these 20 bytes will be again advertised. So again 20 byte packet. So because there is no control here on sender, whatever available window is, sender keeps on sending the data and keeps on triggering the transmission. So if you see it keenly, network will get filled with some tiny segments. So here you can say it's a kind of a conveyor mechanism where you are sending segments. If you are sending big segment, you get big window size open. If you are small segment, you will get a small window size open. And this keeps on happening. And this, they later on realize, led to silly window syndrome. Now, if I ask you a question, if you ask a question, what's the problem with the smaller segment? Suppose I say, so what? Miss, my network is having small segments. Things are going on. Okay, what's the issue if we keep on sending tiny segments? Yes, anybody?
It will create unnecessary overhead because we are decapsulation and encapsulating again and again.
Obviously, because there would be an imbalance between the amount of data you can send and an amount of header is getting repeated. Because in any case, you'll be sending 40 bytes of headers with every small segment. So you always want that, okay, if in any case we have to send a 40 byte segment, means 20 byte of TCP and 20 byte of IP, so you should be able to pack more data with every header. Otherwise, there may be a situation that 10 byte data and 40 byte of header with every packet, and that is just waste of bandwidth. So they realize this, and if you see what's the reason of silly window problem, when either sender transmits a small segment or receiver opens a small window. Suppose you don't have any control at the sender, fine. So silly window or a smaller window can be introduced into system only when a sender transmits a small window or receiver so a small segment or receiver opens a small window. And both are actually interlaced. If receiver opens a small window, sender will transmit the small segment. Or even if the receiver window is big, if sender transmits a small segment, then tiny packet may be introduced. Now, if neither of this happens, the small container will never be introduced in the system. If neither of this happens, then a small container will never be introduced. If you can have control that sender will never transmit a small segment or receiver will not open a small window, receiver will only advertise a big window or sender will only transmit a big packet, then a small container will never be introduced in the system. But is this possible? We can give a try at receiver side. After advertising zero window, wait for a space equal to MSS. Now after closing the window, you should not advertise a small window until unless your data at the buffer is exhausted by the application layer at the receiver side. You always will try to advertise a bigger window. Or you can delay the acknowledgements. But this is not possible all the time. You cannot delay the acknowledgements indefinitely. And at the time of, because if everything is happening fine, every second packet you have to transfer the acknowledgement. And with the acknowledgement, you have to send the whatever buffer space remaining at you. So ultimately, onus lies with the sender. So we'll somehow tackle the sender. That sender should not transmit a small segment or avoid or kind of reduce this particular happening, reduce the chances of this particular happening. Because receiver can try by delaying the acknowledgement that, but that has got its own limits. It cannot delay the acknowledgement indefinitely. So this is a sender's algorithm or Nagel's algorithm where sender is getting controlled. What is a Nagel's algorithm? If there is data to send, but window is open less than MSS, you have enough data, but advertised window is small, less than maximum segment size, smaller than maximum segment size. Then just wait before sending the available data. But how long you should wait? If we wait too long, we hurt interactive applications like Telnet, Counter-Strike, and other instant messaging. If we don't wait long enough, we risk sending a bunch of tiny packets and will fall into a silly window syndrome. Now you'll be able to understand the problem that, okay, you have data, but window is not open. So it's logical to wait for some time so that window can be opened more, but you cannot wait too long. Otherwise, interactive application may get hurt. Or if you don't wait long enough, there is a risk of sending bunch of tiny packets. And then it is nothing but silly window syndrome. The answer is to introduce a timer somehow. Okay, if the timer expires, in any case, you have to send because you cannot wait indefinitely. And you don't wait if you don't wait long enough. So there is a like waiting time. So we have to introduce a timer. And we will transmit when the timer expires. Now, what is this timer thing? And this is the beautiful part of Nagel's approach. Nagel introduced an elegant self-clocking solution. The idea is that as long as TCP has any data in flight means data which has been sent but not acknowledged. So this gives an idea. Suppose let's take a snip. What is the solution? Suppose I'm a sender and I'm getting data from my application. My window is smaller, advertised window is small, but I do have some data in flight. I do have some data in flight. Means the packets which I have sent but not acknowledged. Now this is a intuition that eventually I'm going to receive acknowledgement. And this acknowledgement can be treated like a timer firing, which can trigger the transmission of more data. So everything is dependent upon that whether you have any data in flight or not, because that's an intuition that if data in flight is there, eventually we'll get some acknowledgement and some latest situation about the window at receiver through that acknowledgement, which may help us in triggering the transmission with more data. Nagel's algorithm provides a simple unified rule for deciding when to transmit. Now, what is that simple algorithm? When the application produces data to send, if both the available data, now pay attention please. When the application produces data to send, if both the available data means you have accumulated enough data from the application and your available window is both are greater than maximum segment size, then send a full segment. This is the case where you can send the full segment. If there is unacknowledged data in flight, then don't send. Buffer the new data, keep on buffering the data from the application until an acknowledgement arrives, which acknowledges all the unacknowledged data in flight. If new acknowledgement arrives, which acknowledges all the data which is in flight, means there is no data in flight, then trigger the transmission. If both of these cases are not true, then whatever you have accumulated, send now. So this is the very simple Nagel's algorithm. If you have data from application, your window is also open more than MSS, send the full segment. If your window is not open up to MSS, or maybe it is opened Fine, but you don't have enough data in both of the cases. Now this is the third case. Your window is opened. Fine, but you don't have enough data, then you have to send in any case. If there is unacknowledged data in flight, keep on accumulating the application data and fire the transmission when acknowledgement arrives. Otherwise, send all the data now. Now, we can turn off the Nagel's algorithm also by using TCP underscore no delay option. When you create a socket in your socket programming, you can use this particular option. And for a certain application, suppose you don't want to delay your application client and server and like that they don't want to wait. Whatever data is created, send that moment only. Then you can switch off or turn off this option Nagel's algorithm by using TCP underscore no delay option. Now, after applying these rules, they have observed that tiny packet problem was somewhat resolved. An idea is very simple. It's just that it was a timely idea, and that's why Nagel got so much popularity. Because before that, nothing was specified in the standard, and the standard was silent about it, when to trigger the transmission. And because the standard was silent, different implementations have you know, coded the TCP in different manner, which resulted in silly window syndrome. And then a small self-clocking mechanism is applied by Nagels, and we could solve the problem. Fine. Now the next issue is protecting against wraparound. Please be with me and concentrate. We know that we have 32-bit sequence number space. Sequence number used on a given connection might wrap around. Wraparound means byte with sequence number X could be sent at one time. Then at a later time, a second byte with the same sequence number X might be sent. Now this we have already seen when we were discussing GBN and SR. Fine. Now there are certain assumptions. Please be very attentive. If we assume that packets cannot survive in the internet for longer than recommended MSL, maximum segment lifetime, which is, I don't know what is the current situation, but as far as I know, it is 1/22. Means a packet can be considered live up to 1/22, and that is calculated from one end of internet to another end of internet, and they have calculated and given this, okay, maximum segment lifetime should be 1/22. Let us check what is nowadays value of MSL. Maximum segment life value. Now it is normally 2 into MSL, that is 60 second means uh, MSL is 60 second. Okay, so 1/22 may be reduced to 60 second. You need to check it later on at what is the current value now. But the book which I utilized to make these slides, they have considered that maximum segment lifetime is 1/22. But value is not important. The important thing is we need to make sure that sequence number does not wrap around within 1/22 period. Why? And forget about 1/22. take it some, suppose I say the MSL is some t seconds, means MSL is maximum segment lifetime, means the packet segment may be considered live in the internet for maximum t seconds. And then we need to ensure that our sequence number should not wrap around before t seconds. Why? Now I'll tell you, suppose a packet has started its journey. Packet has started its journey. Now maximally packet can stay in the internet for t seconds. Means packet can surface at the receiver, can surface at receiver, and the maximum time for that is t seconds. Now if your sequence number wraps around, space wraps around in less than t seconds, then what will happen? Packets with same sequence number may be live on the internet. This is also X and this is also X. And they both may surface. One, say after t minus 1 second, and this so what will happen here, that if the wrapping around is happening before the maximum segment lifetime, then there would be a problem of disambiguation. How to clearly identify whether this is the packet or this is the packet. That is the benchmark of finding out how to protect the wraparound of sequence numbers. That is protection again, wraparound sequence. If we assume that packets cannot survive in internet for longer than recommended MSL, we currently need to make sure that the sequence number does not wrap around within a 120-second period, which is the recommended MSL when these slides were made. Now, if you see the bandwidth of different lines, now if your bandwidth of channel between source and destination is 1.5 Mbps, it will take 6.4 hours until wraparound. In Ethernet, it will take 57 minutes, a lot more than 120 seconds. If you have T3 lines of 45 Mbps, it will take 13 minutes. If you have fast Ethernet, 6 minutes. And in your institute, we don't have fast Ethernet. We have gigabit Ethernet, means 1 Gbps link. So if you have 622 Mbps link, it is 55 seconds. If you have 12.5 Gbps link, it is 14 seconds. So you can see, normally in Ethernet also, we have gigabit Ethernet nowadays of 1 Gbps. It will be way less than 120 seconds. So your sequence number is wrapping around very quickly, and which may create problem and may result into TCP reset. Now, how to extend our sequence number field? Please be with me. And this is going to be implemented as a TCP option, the way we have implemented SAC option. How it can be done? Define a new 64-bit sequence number field, where 64-bit is not the complete sequence number field. TCP uses 32-bit timestamp to extend the sequence number space. 64-bit sequence number is not going to be used to be given to the different bytes. Bytes को अभी भी 32-bit sequence number दिया जाएगा. Now this 64-bit can be deciphered as that has a sequence number field in the low order 32 bits and the timestamp in the high order 32 bits. And as we know that timestamp is always increasing. Now, if that is the case, so if we take this example, this packet and this packet, maybe both are having same sequence number, but both would be having different timestamp value. And in this way, you can easily distinguish between these two packets that whether they are two different incarnation of the same sequence number. Timestamp is being used in this setting only to protect against wraparound. It is not treated as a part of sequence number for the purpose of ordering or acknowledging data. So maybe acknowledgement number and sequence number would be of 32-bit, but this timestamp value would be taken at would be used to identify if that those lower order 32 bits are same, means the sequence number is same, then we'll go and see the timestamp value just to distinguish between these two different incarnations. And this is implemented as a header options TCP extension for PAWS. Now the second problem, 16-bit advertise window. If we assume that round trip time is 100 millisecond, RTT is 100 millisecond for all these lines, you can see this 16 bits advertised window is actually worse shaped than the sequence number field. If 100 millisecond RTT is there, then for line with 1.5 Mbps bandwidth, we take delay into bandwidth product. So in at one time we can send, in one go we can send 18 kilobytes. In 10 Mbps we can send 122 kilobytes. In 45 Mbps we can send, now if you reach to 1.2 Gbps we can send 14.8 MB data in one go. Fine. And this is the actual pipe size. This much data can travel in one go. But if you see the TCP advertised window field is worse shaped than its sequence number field. It's not even big enough to handle even a T3 connection. T3 is 549 KB. If you take 16 bits and means 2 to the power 16 bytes are there. 2 to the power 16 bytes is, if you calculate, it is 64 KB. So what is happening that advertised window size is not allowing you to utilize the complete bandwidth. Means if you see the case of 1.2 Gbps bandwidth with 100 millisecond RTT, if you want to keep the pipe full, you have to send 14.8 MB data in one go. But this advertised window size can allow you only 64 KB. That's the issue. That's the issue. You are not able to utilize the bandwidth completely, and that is waste of resource. Window scaling is the another TCP extension to advertise a larger window to fill larger delay into bandwidth pipes. This TCP option defines a scaling factor. It's very interesting. Interpret differently the number that appears in the advertised window field. You can just change the unit. In normal situation, if suppose advertised window suggests that 100. So in normal TCP, Without any window scaling option, 100 will be considered as 100 byte.